It's really a pleasure to introduce Mohammad Hafezi here. Mohammad is a dear friend from the University of Maryland. We have talked physics countless of times. We also had some drinks a couple of times.
Countless.
He's saying. Mohammad started his career if we call PhD the beginning of the career. It was at Harvard, where he was a theorist in Michel Lukin's group. He graduated in 2009. If you want to dig deeper, then he's a graduate of École Polytechnique, right? Which is a military school.
That's right.
So if you see certain mannerism associated with that, then that's where it checks back to.
I didn't bring my sword.
He graduated in 2009, he became a postdoc at fellow in JQI in Maryland. And at that time, he came up with the groundbreaking idea of how to have topological photonic states, but nobody wanted to do the experiments. So he decided, well, why not I do the experiments? And became a part-time experimentalist and successfully showing the first topological photonic state in an array of oscillators, array of waveguides. So he became faculty in, we couldn't agree whether it was 2014 or 15, but he has been in Maryland ever since. Every couple of years, he invents himself anew, not just moving from theory to experiment, but then propelling himself to the forefront of experiments on the combined transport and from interaction with light, all throughout keeping deep involvement both in theory and in experiment and in a variety of topics that include all elements in the statement strong light matter interactions. So any element together and separate have contributions from common. So I can go on, but I won't. I'll just say Mohammad was a recipient of several prestigious awards, including Department of Defense Early Career Grant, Simons Investigation, Sloan Award, and I'll stop there because it might continue. So please, Mohammad.
Okay. Thank you, Gil, for the invitation. And I'm glad to be back. I know many of you, and it was hard to make a talk that would appeal to everyone. So I kind of made a mishmash and a mix of things. I hope it would be interesting to all of you. So the pitch that I'm doing today is that I would like to kind of try to convince you that we have a new era of quantum optics. I'll spend one slide to explain what I mean by quantum optics. And in particular, I would like to convey this message that we have a lot of advances in quantum optics thanks to quantum information sciences, making quantum simulators, making quantum sensors and quantum networks. And I would like to say some of these ideas, both theoretical ideas and experimental techniques, could be used back on material to manipulate material, to probe, manipulate, and control many body states of electrons. So basically, things that we know how to do for qubits, etc., to what extent we can bring them back to a material and then look at interesting phases of matter, manipulate phases of matter, etc. So that's kind of the big goal of this, and we will see how much I can succeed in that. Okay. So quantum optics, you had a very esteemed colleague, Jeff Kimball. So maybe a word to his memory. The way to look at this quantum optics is to look at these in terms of two axes. One axis is the number of photons involved in the system, and the y-axis is the strength of interaction per photon. Basically, the fine structure constant. How strong the light can interact with matter, and that's usually very weak. We know that light-matter interaction is very weak. So most of the regimes that we are interested in and we occur in nature is in the linear optical regime. There are not many photons, the light-matter interaction is weak, and we're in the linear optical regime. If you put many photons in the system, the same weak interaction, you get to the classical nonlinear optical regime. This is the regime of solitons, optical solitons, nonlinear Kerr effect, etc., etc. And another way to see it is that you have a two-level system. It interacts with light. The cross section is lambda because that's the only relevant length scale in the system. A is how much you can focus your light, and typically that number is much smaller than 1. So the way people got around this is that they put it in a cavity such that the light is trapped and it has many chances to interact with the atom. So basically you amplify that probability by the number of round trips that you can do in the cavity, and that's called finesse, the number of round trips that you make in the cavity, and that can be larger than 1. Another way to see it is that G is the strength of the coupling of two-level atom to this cavity. Kappa is the decay rate of the atom. Lambda, gamma is the decay rate of the atom. So if that number is larger than 1, we say that we are in the regime of cavity QED. And if you have many photons in that, then we are in the regime of many-body cavity QED. So the talk will be about, can we find some interesting physics, even classical, that we are actually inspired by quantum information or even condensed matter, in particular topological physics, that some of it is actually even classical. We could have thought about it at the time of Maxwell, but it didn't occur to us. We had to do it through a loop of quantum Hall effect, condensed matter physics, topological orders, topological phases, and then coming back to photonics. And the other part is that, is there another access to this plot that I have shown? Because as you can see, why the hell I put these axes like this, because later I would like to introduce another axis, and that's the axis I give a spoiler, is the strength of electron-electron interaction, if we include electronic correlation in the system. If we go beyond this two-level atom or two-level center, color center that is interacting with light, if I'm dealing with itinerant electron in a system, can I manipulate them? Can I look at interesting phases of that? So the first part of the talk will be kind of classical, and then I will tell you how it kind of led us to this new part that is the quantum optics of correlated method. So that's the plan. So if you want to sleep for the first half, feel free. Okay, so in order to talk about topological photonics, I just start with what is the fundamental building block of a photonic system, and that's a resonator, a ring resonator, for example. That can be in the optical domain, in the telecom regime, in the microwave domain. They can be linear, they can be nonlinear, like superconducting qubits. You can think of them as just nonlinear resonator. You can have them on silicon oxide. These are rings that are made on rings of silicon on silicon dioxide. And then we're interested in interesting properties of that. So to have that in the back of your mind, when I'm talking about photonic lattices, it can be generic in material and frequency. Okay, topology, I don't need to describe too much. Basically, topology has to do with when objects have the same topological property, we can deform them without gluing and pasting. Usually people show the coffee mug and the donut. I have another example. It's not as illustrative, but I hope just as a change. So all islands are topologically the same. That's why we use one word, island. If they're connected to the land, we use another word, peninsula, okay, almost an island. So they're topologically distinct, that's why we're using the different words. So regardless of the shape of this island, we call it an island. So what? Now the idea is that if I swim this around this island, sorry for the topological experts in the audience, this is just for fun, let's just relax. If I swim around this island, I can go clockwise and counterclockwise. And if I come back to the same place, I do a random number of round trips that is an integer number, right? A positive or negative, but it's always an integer number. If I want to do that for the peninsula, it's always 0. So I have assigned an invariant to these island and peninsula to differentiate them. So the whole point of topology, in a very a pedantic way, is that if you relate the topological, if you relate a physical observable to these integers, then you are guaranteed that that physical observable is robust against some kind of perturbation. So here, the shape of the island has nothing to do, does not change that integer. The way that you're crossing around it doesn't change. So the whole kind of game is to find what that physical observable is that is insensitive to those deformations. And I will be quick about this. The way that the topology entered physics was through quantum Hall effect. You have a two-dimensional electron gas, magnetic field perpendicular to the surface. You look at the transverse resistivity as a Hall resistivity. If you look at it as a function of magnetic field, you see that the Hall resistivity exhibit these plateaus, while the longitudinal one shows these suppressions. Okay, and what was remarkable is that the value of these plateaus is just given by some fundamental constant, which is h divided by e squared, and n is an integer number. So it's a remarkable effect, and to my knowledge, it has been the only robust manifestation of topology in physics. The rest of them has not been super robust. Although theoretically they have been predicted to be robust, and now it's a standard for resistance. The reason that they're robust, and we'll talk about it because of the presence of these edge states. And then the question that we asked several years ago was that can we have the same kind of physics for photons, and if so, if it's useful, why? Because generally in a photonic system, you have a waveguide and then you have some disorder. And if the photon is propagating and the scattering of this disorder, it will back scatter. But then if it's topological, when we encounter this impurity, it will not scatter in the bulk or backward. It will go around the impurity and continues its way. Okay, so the same way that these edge states are robust in the quantum system, it should be robust in photonic systems. And as I said, these are the robust solutions of the Maxwell's equation. That's fine. So as I said, Maxwell would have thought about it. These are the classical solutions of the Maxwell's equation, but it took us to go to quantum Hall effect to translate it into back to photonics and then appreciate the presence of the solutions of the Maxwell's equation. So one way to make this to simulate the effect of have topological effects in photonic systems to consider these arrays of ring resonators. And we would like them to feel the same way that the electrons feel in a two-dimensional electron gas. That you have a magnetic field, and if the electron goes out, magnetic field acquires a non-zero phase. So if you can come up with a way that these photons, when they hop around a resonator from one resonator to another resonator and close the loop, should acquire a non-zero phase. The way to do it is very simple. You take two resonators and then couple them with another resonator that is off-resonant. And then you place this middle resonator as a little bit asymmetrically. So when you're hopping from this resonator to another resonator, because these are directional couplers, you take the upper path. And then when you're hopping from this one to this one, you take the lower path. So when you're going from left to right, you acquire a phase that is different than when you're hopping from right to left. And since the Hamiltonian is Hermitian, you're guaranteed that that phase is exactly equal and opposite. So now once I have this, I can stack these resonators in such a way that I can implement a gauge field that corresponds to the uniform magnetic field. So when you make these asymmetric pattern in a good way, then it would correspond to the same phase when I go around the plane. So this Hamiltonian, a uniform magnetic field for a square lattice, the spectrum of it is known as Hofstadter butterfly. So if you have a system on a torus and periodic boundary condition, you have these eigenstates for a fixed magnetic field. So magnetic field is characterized by this alpha. Then you have these states, and then if the system is not on a torus, it's not periodic boundary condition, you have some states that appear in between them. So that's the theory. The experiment, one can actually use silicon and insulator technology to build these arrays of ring resonators. So this is an actual image of resonators coupled to each other, but these are asymmetric. You can barely see the asymmetricity because the scale is 30 micron while you're operating at 1.5 micron wavelength. So they're shifted, believe me, but that's enough to create this gauge field. And now, if you have this, if you put it on a square, then you have these edge states that are going either in the clockwise direction or counterclockwise direction, and they have different energies. You can think of it as you have a uniform magnetic field, and then if the electron has positive orbital angular momentum, it has a different energy than if it has the negative orbital angular momentum. What does that mean? It means that if I have some impurity over here, when the photon comes here, it would like to backscatter, but the backscattering state has a different energy. So the backscattering is suppressed because I have to go through so then I have to go through help me inelastic scattering. I have to change my energy to backscatter, but that's not possible in optics. Usually they're very, very weak. So this is an experimental implementation. You can actually remove one of these resonators. You don't need to even put these over. Just forget about one of these resonators. And then you see the photon comes here. We send the photon that is resonant with these guys. The photons comes here. It will propagate over here, and then it would go around the impurity and then continues its way instead of getting backscattered or going to the bulk. So this was the experiment, and this was a theory from many years ago. And that was supposed to be just a quick introduction. But if you're interested in more details and around, so that platform allowed us to not only see these robust edge states, really image them, but also measure the corresponding topological invariant, which is the winding number. So you can actually perform the spectral flow. You can pierce a magnetic flux into the hole. Everything is synthetic, so you can do whatever you want. You can make something like a Haldane model. You can stagger the magnetic field, so uniformly, like the magnetic field is on average zero, but it has negative and positive sides on different sides. You can make topological lasers out of it, and then you can make them reconfigurable. This is one platform that we have been using, but there are many groups around the world that are using other kinds of platforms in different frequencies, different material. There is a huge number of papers and activities just exploring these ideas. Now, going back to my quantum optics chart, is it possible to just move away from this linear optics that I have shown so far and then go and explore other regimes? Because what I showed you for this quantum optics applies to anything that you do in optics. So we're doing topological photonics, it is applicable as well. So here, I have the same axis. This is photon-photon interaction, because photon-photon interaction in the end depends on photon-matter interaction. You just integrate after matter and then gives you photon-photon interaction. And then the x-axis is the photon number. So what I just described is this linear edge states. And then we have, if on this axis we introduce a strong interaction between photons, we can think of a fractional quantum Hall state of photons. And then if we go in the linear domain, we can have solitons that I will talk in English. So before that, just explain how we can explore some quantum regime. Just one slide on the introduction, how you generate photon pairs. So imagine that you have a ring resonator, you pump light, you absorb two photons, and then you emit two photons. They don't have to be the same frequency. The only thing that you have to conserve is the energy and momentum. So the sum of the incoming photon frequency should be equal to the sum of the outgoing photon frequency, and also the momentum of them should match. So the sum of the incoming photons should be equal to the sum of the outgoing ones. This is usually called as phase matching in optics, but it's really a momentum conservation. So you pump the system, and then you generate a photon with higher energy and lower energy, and this is your Hamiltonian. And people use this to generate pairs of photons in many systems, silicon nitride, silicon, lithium niobate. This is a way to go. But if you want to increase your yield, you want to pack these resonators next to each other so that you get more pairs of photons out. But as you know, any nanofabricated device has disorder, so you can think of them as this as a 1D Anderson model that you have disorder on each side. So if it gets longer and longer and longer, at some point all the states become localized, and then you don't get anything out of it. If your system size is a little bit below that, what you get is that you get device variation. So these are the spectral function of the emitted photon from one device to another device. So naturally, you see that they change from, okay, this is not reflected, this is reflected. But from one device to another device, I see a huge variation. That's normal because of disorder. But can this topological protection actually help us? Because we know that topology provides us with this very nice, robust edge states. So the idea is that you have your pump over here, and then you have, these are the longitudinal modes of the resonator. But then we have an array of them. So each of those longitudinal modes will split into many little bands. And in each of these bands, we have the bulk band, you have the edge band, etc. I hope that's clear. So if I had just a single ring over here, these modes correspond to different longitudinal modes of this. So it will go to infinity on this side and then 0 on this side. But now, if you have two resonators coupled to each other, you will get two modes, and then two modes and two modes. If you have n of them, you would have n modes here, and n modes here. Is that clear? Or should I do quiz? I'm not allowed. So now what we have is that the edge state repeats itself across the spectrum. So if you have edge state over here, you would have edge state over here, edge state over here, etc., etc. So if I pump one of these edge states, it will generate higher frequency photons and lower frequency photons into the neighboring modes. And if you look at the transport properties of these edge states, if you just look at the transport for photons, means that you measure how much of the photon is transmitted or how long does it take for the photon go through the system. See that if the photon is resonant with the bulk, you would see that from device to device, different curves correspond to different devices. You see a huge variation. But when you go to the edge, when you excite the edge of the system, you see a robustness, both in terms of the time that it takes to go through the system and the transmission. So this is like a statistical way or the corresponding transport measurement that one can do in photon. And then you see from device to device, you see a strong robustness. So what we do is that we pump one of these in one band, and then we generate photons in the other corresponding edge states. So this is the 1D, where we do 3 devices, and then we see that the spectrum changes a lot. But when you do it for 2D, yes?
To make sure that I understand, so when you say edge case, you mean just the outlier of like some of them, these resonators that you probe?
So I always excite the system, thanks for the question. I excite always the system at the edge, but then I choose the different frequencies. So if I'm resonant with the bulk, my photons will go to the bulk and then come out.
So when you say edge state, it's not a geometric, that's what I get.
It goes around the edge of the system.
Yeah, okay.
So it has a specific frequency band. So when I was showing the Hofstadter model, for example, so I always couple, let's say from here, if I'm resonant with these states, then I will go to the bulk and then I may come. If my frequencies resonate with the edge state, then I go through the edge and then I come out, or maybe I circle around a few times. Any other question?
Then you mean that this is robust because of the topology of this?
Exactly. So as I said, it's just a solution of the Maxwell's equation. But if you like on a very high level, the solution of the Maxwell's equation should be single valued. Basically, the phase of the electric field when I go from here to here, it should come back to itself with 2 pi. So now, if you have some deformation, if you put your foot on some part of the chip, this photonic node should deform itself such that it would compensate that extra phase that has acquired somewhere with somewhere else, such that again it will come back to 2 pi m being an integer number. So that's kind of like the intuition. But if you didn't have the magnetic field, then this states and this states would have the same energy. So there is no constraint on the phase change. So here we are kind of locked in. It has to change by an integer every time. It's a very stupid intuition, but I don't know. We didn't think about it for centuries. Okay, but if I'm moving, it's actually robust. So when you go from device to device, you see that the photons are coming out at that specific frequency that corresponds to the frequency of the edge. And then all this is happening while that our magnetic field is fake. So it's not uniform, it changes from side to side. Nevertheless, we have some robustness in the system. We're not, we don't have a magnet, it's really this simulated phase. And yeah.
Understand. So in your case, all effect magnetic field breaks Stammeros invariance.
Right.
So what's the source of Stammeros invariance breaking?
Very good. Someone caught that. So each resonator has two modes. So I have a clockwise and counterclockwise mode. So this magnetic field, and we can think of them as like spin up and spin down. So this fake magnetic field that we have generated is positive for this one and negative on this one. So basically, we have two copies of Hofstadter butterfly with different magnetic field. Now the catch is that we come with a waveguide that only excites one of these modes, and the material is in such a way that we don't have a mechanism that flips the spin from this circulation to another circulation. The example of it would be a magnetic impurity in the topological insulator. So here we don't have a term. Like imagine that I have some impurity on my resonator that would flip the sign of circulation. Then I would have gone to the other copy of the quantum Hall, and I would not.
Well, how do you like, choose which way it goes?
Very good. Whether it goes this way or that way. So if I zoom in here, it's really like this. So the photon is coming like this, and there is a momentum matching between the waveguides. If we had designed it to be like this, then both of these would have been excited. Yeah. This was the part that no one kind of believed this would kind of work. Because in any fabrication, you would have also some disorder that would flip the spin, and then we would get no protection. But it's just, I have to do an experiment and see whether those disorders are relevant or not relevant. Again, like a TI, we didn't think that they would be so susceptible, but they are susceptible in the end. So here it was the opposite. These disorders are not relevant. Otherwise, we could not see any of these.
More obvious way to break Stammeros is actually magnetic field.
Very good question. That brings me to some anecdote. So when I was writing this paper with my co-authors, I looked online. I did not do a literature review first. I did like a bad graduate student or postdoc thing. So I always wrote a draft, and then I saw on the archive there is a paper by a famous physicist called Duncan Haldane that talked about this problem with the magnetic field that actually breaks down universal symmetry. And it was so sad. I spent like 2 years to figure this out, and then Duncan has a paper on it. But the catch is that the magneto-optical effects are super weak, especially in the optical. So there is no way that we can actually have this as a strong effect in the visible light and many of them. But then once we realized we can synthesize it, then a lot of things came up, because then now we can synthesize, we can do it in different material, etc. And that's why the paper got popular. Otherwise, there was actually a paper by Duncan. Thanks for the question.
So you have to break the symmetry by the initial pulse.
Correct.
Because you choose the.
It's like injecting a polarized current, basically.
That's what it's symmetry.
Exactly. So it's not really a quantum Hall model, it's like a spin model. So you have two copies, but then I just inject it with a spin off.
Non-equilibrium.
Exactly. Yeah.
But I think in microwave range, you actually have more symmetry, you have much larger effects magnetic field.
In microwave regime.
Yeah. Into visible light.
In contrast to the visible light, correct. Yeah, when you go to lower frequency, the magnetoptical effects are not.
In electrons, the edge state is actually a continuum. So why do you have discrete state?
Because we have finite number of resonators. So if I have 20 resonators, then I would have 20.
This is quantization.
Exactly. So that's why, actually, that you're asking a question. So that's why we could do a spectral flow. Because imagine that this is my edge, right? So now it's quantized because I have finite number of modes. And I look at the transmission and I pierce the flux and I see these resonances in the edge flow this way or that way. Because of finite size effect, actually, we could do spectral flow. Any other question? You're doing great with time. Okay. That was just generating photons, pairs of photons, and we saw there is some robustness. There is another aspect to that. If we take the same Hamiltonian and then drive it very strongly, that gives us the optical frequency comb. So what is a frequency comb? Very quickly, is that you want to have light pulses that are separated with the same amount of time period. And if you take the Fourier transform of that, you will get light pulses in frequency that are separated with the same frequency. And this is like a ruler for time and frequency. It's very useful, of course. The way that you take a nonlinear crystal, you shine CW continuous wave light, and then because of some nonlinear process, you generate these frequency combs. And there is a big effort on miniaturizing, because this Nobel Prize was for just big frequency frequency comb. There is a big effort to miniaturize them and bring them on chip. There are of course works on this campus on this, and I think Tobias was the former postdoc here before going back to Europe. So there is a very nice review if you're interested in that. Generically, is this you have a ring resonator, you pump it with the laser field that has one frequency, and then what comes out is this beautiful comb. Now, this comb is very low efficient, has low efficiency. You have to put a lot of power in it. Second is that it doesn't have any feature. It's just these guys that are equidistant. If you want to have a ruler that has different peaks, like I don't know, two peaks very away from each other, but then when you look at each peak that has a higher resolution, you cannot do that. You just have one length scale in the system, and that is the length of the resonator. So can we do such a thing? And of course, we have a topological hammer, and we are going after it. So it is the same Hamiltonian that I introduced before. It's just we were generating just pairs of photons, but now if I crank up the intensity higher and higher, you generate more sidebands. And each of these sidebands, they can generate their own, etc., etc. But it has to be a very fine balance between the mean field shift, because you put photons in each mode, and it will do a mean field shift, just simple Kerr nonlinearity. But there is also dispersion. So this dispersion and nonlinearity kind of conspire such that they will lock and they will come out at the same frequency. And then what we want to do is that we want to consider an array of them. And then with these arrays, we would like to use topology to help us to do the phase matching. So just a very brief introduction of a frequency comb for a single ring. If you just have a single ring and then pump it with a frequency that is on the x-axis, the cavity, the power in the cavity will exhibit something like this. So if you're at some frequency, you will generate this soliton. So if you look at it in time, it's a peak in the resonator that will go around the resonator. So if you take the Fourier transform, it will give you those peaks that I said. If you bring it somewhere in the middle, it would be chaotic. It's a nonlinear problem, nonlinear mode, so it's generically it will give you chaos. And if you go to some other region, you generate some other pattern. So they're called Turing patterns, because Turing thought about how animals and creatures will develop patterns and stripes by introducing some dispersive nonlinear differential equation. And basically, this is it. You have some dispersion, and you have some nonlinearity, sometimes there are these periodic patterns that emerge. So they emerge the same way. And unfortunately, they're very inefficient, meaning that most of the power that you put in the system is lost. Only a very small fraction of it is turned into a frequency. So this is our model. So it's the same Hamiltonian that I introduced previously. So it has some hopping with some phase. Here it's more like a Haldane model. It's a staggered magnetic field compared to a uniform magnetic field that we had in the past. Added this nonlinearity. So you kill two photons at mode 1 and 2, and then you generate them in mode 3 and 4. Meanwhile, you have to preserve energy conservation. That's why we have that Kronecker effect. Okay. So we solve this model in the mean field regime. So basically, it's just the mean field solution of this Korosky-Tversky equation, if you like, with basis. It's called Giatrio-Lefebvre equation. And then this is what you get. You get this frequency cone that they are around each resonator, but then it has a general structure that it's not only a soliton in each resonator, but it's a soliton in the super ring resonator. So there are two time scales, one time scale in each resonator, that's the fast time scale, and then another time scale that is going around the edge of the big system.
So
yes,
this may be just an optical illusion or a trick of perception, but it looks like it pauses at each corner. Is that real, or is that just my eyes playing games?
no, because it's not circle, so it's not smooth. That's why. But also it's not a real-time solution, because otherwise, if I resolve it, each of them should also oscillate at a very fast frequency. So this is a spectroscopic kind of, and it's a simulation. It's not real data. And then they are robust. They're the same way. So if you have one of the resonators removed, they will go around the edge, etc. And we can make a phase diagram because we're physicists and we like phase diagrams as a function of different parameters. So this is the detuning of the pump. This is the power of the pump. You have some chaotic regime, you have some Turing rule, and then you have this super soliton that I mentioned over here. We understand this numerically. We don't understand it analytically, or we don't have like a nice phenomenological model to understand. I think we don't even have like a bulk edge correspondence for here. In a linear system, we have bulk edge correspondence. When you put the system on a periodic boundary condition, you calculate some invariant, you make the system open, you should have edge states if that invariant is non-zero. Here we don't have an equivalent, and that's an open theory question. Experimental realization, it took us 4 years to show it. Not we, actually, my graduate student, Chris Flower, who proudly finished this towards the end of his PhD. The system looks very similar to what I showed you in the previous slide, but it took a lot of iterations actually to get to this, because we're going from linear physics to nonlinear physics, and it's not easy to get this working in terms of the design, the powers, anyways. So I cut this short because I would like to get to the second part of my talk. If we start pumping the system and cranking up the intensity, we'll see the emergence of this frequency cone. As we increase, we see these teeth appearing. And then if we zoom in one of these peaks, we should see an extra structure on top of that. Remember, there are 2 time scales in the system. One short time scale, which leads to large frequency spacing, and then one slow time scale that goes around the whole system that should show us like very tiny teeth on top of this. So, of course, the referees were not happy with this because we cannot really see those things. My industrious postdoc will found the spectrum analyzer that we could get for demo for free. And we did more experiments with the demo, and indeed, their results. This is like a very fancy spectrum analyzer that now we just over there. So they're okay with that. So you can see that not only we have these ones, but when we zoom in, you see this beautiful nestedness. So you have one peak here, and then if you zoom in, you have these nested ones appearing. Now, if I park the pump in a different frequency when I'm in the bulk or if I'm in a single resonator, we don't see such a nestedness. We only see this nestedness when we are in this topological system. We can also image it, meaning that we can pump the system, filter the pump, and then just image the system on the sidebands. Then we see once we excite one of these edges, these are simulations. You see that the comb is generated at the edge of the system. Then when we're pumping the bulk, we are generating the pump. So this is demonstration of these nested comb. What is missing is to show that they're actually synchronized, that they're solitonic behavior, that I can have different frequencies coming, but they're not locked to each other. So what we have not shown when we have some preliminary results is that we can show that they're actually locked and then they can perform as a solitonic things. And we're wondering whether it's good for a nested, this nestedness is good for spectroscopy. Imagine that you have some molecules that have some resonances, but they're very far away from each other, but you want to have high resolution around them. So we had some discussions with the spectroscopist, whether it is useful. This is a very highly nonlinear system. When we're solving this differential equation of many resonators, it takes a lot of time. And it makes you think that, oh, okay, so it has a lot of computational power. So maybe you can do the other way around, and you can use it. You can use the computational power of this optical nonlinear system. Okay. So with that, let's summarize the first part of the talk. So what are the directions? I said here we have these directions. Of course, we can go to this topological regimes when we have now interface it with matter. So far, we were just talking about light and so solutions of the Maxwell's equation. But imagine that we hybridize it with some matter degree of freedom, and we can even go further. Can we have so here this is linear and weakly interacting excitons that are exhibiting topological behavior? If you have questions about this, you should ask the inventor of it in the audience. Well, can we have excitons that strongly interact with each other? So this is a theory proposal that we had with Shankar and Ming Shi, whether we can have, for example, fractional quantum harmonic states of exciton if they strongly interact with each other. And more generally, can we have this interplay, topological interplay between photonic and electronic topological state? Can we use light to measure the topology of an electronic system? Can I use light to manipulate it? Can I use light to braid angles, things like that? So these are big questions that we're trying to come with at different angles. And even also when we make them, how do we measure them? So in superconducting qubits in the microwave regime, they're already strongly interacting. So if you have a synthetic cage, how can you measure it? And this is an interesting question. If I don't have access to a torus or linear transport, or basically, if I'm not within the linear response paradigm, are there different ways that allow me to measure topological invariance? So, that takes me back to this one. Now we're interested in electrons and bringing now the electrons back to the game. So if the electrons are bound and form a two-level system, then we are over here. But if the electrons are right here, then you can have a correlated state of electrons. You can have all kinds of interesting states. And then this led us to write a perspective a few years ago with these colleagues. And this is actually this axis that you can now explore now correlated material. Can we use this quantum optical approach that I said in the beginning of my talk to manipulate, probe, and control different states of electrons? Can I make can I induce superconductivity? Can I enhance superconductivity? Can I have optically induced magnetism? Can I optically have a Heisenberg model, like shine some light, etc., and then engineer a Heisenberg model? Most of these things from my side is motivated by what we have learned in cold atom. It's beautiful experiments that have been going on in the cold atom community, that you have two-level systems of atoms, and then you have an optical lattice, you trap them, you cool them, you engineer any Hamiltonian. So the dream would be that, can you do that for electrons? Can you like cook out whatever Hamiltonian you want optically and then implement it on the electrons and then use them? So that's basically where it's going. And in order to get there to those big questions, one has to answer simple questions. One question is, can I think of these atom and electron as two-level systems that are coupled to light? The answer is no. And I cannot do my usual two-level atom approximation. In other words, I cannot do the simple dipole approximation, and I will tell you why. What is the equivalent of James Cummings model? When you're dealing with atom and electron, how can I talk about strong coupling? Because it's those G and gamma and kappa are not there anymore. Can we make optical lattice for electrons or excitons or trions the same way that we have in cold atom? Can we? How should we think about elementary excitation, optical excitation in a correlated material? In a semiconductor, you have a valence band, and a conduction band, and then you have electron and hole, and they bind and they form an exciton. My conduction band or valence band are in some correlated state. It's a Martin oscillator upstairs and a fractional quantum downstairs. How do you think about that? And how do you probe electronic correlation functions with photons? So isopatrically entering here, you have a very old, like maybe 15 years ago, on how to measure different spin correlators with Raman. So can we extend that with now quantum optical techniques? If I measure now quantum correlators like squeezing and anti-bunching, etc., can I measure higher orders of S plus S, etc., etc.? So we have a mix of theory and experiments on this front, and 10 minutes, right? So the talk has, so those 4 questions that I put, we have partial answers to them. The quick answer is that dipole approximation does not work. One has to be quite careful. Optical lattice for 2D material, we can do it. We have some preliminary results, how we can create an optical lattice for the excitons. Excitons in TMD or in correlated material, how we should think about these excitons in correlated material, we have some answer, but it's still really ongoing. This is actually connects well with what Dave is doing here. And then what I just talked about optical probe. Okay. So what should I do? Chair.
You mean we have to choose between these 4 topics, or?
I think so. No.
Exciting.
Yeah. Okay.
Yeah, think about.
Yeah, teachers. Saying this because this is probably a little bit fundamental, so maybe I will start with this one. But dipole approximation. Light matter interaction, we do dipole approximation because the atom is small compared to the wavelength of light that is relevant to that frequency, so it's good. So in solid state language, it means that there is no transfer of linear or angular momentum to your electrons. But what if my electronic wave function is big compared to the wavelength of light? That happens in one hole. We have these edge states or extended states that are big. So if they interact with lights, maybe they deviate that. So in an atomic system, you can actually look at it like S to B transition is allowed, P to D transition is allowed, but S to D is very big. It's possible to see that, and there's a beautiful experiment in Mainz that showed that that's the case. And the way that is possible is that you have to give electron an extra angular momentum, which comes from light. So not only it has polarization, but also orbital angular momentum. And they did this beautiful experiment. They could see direct single photon S2D transition. Can you do that for an excitonic system? Yes, it is possible. If you shine light from ground state, then you will create a 3 exciton. And then normally you would think that that would be a very large effect. But what we understood is that, well, we did some initial experiment, we didn't see anything, a bunch of groups didn't see anything. And I think that the resolution is in this paper is that imagine that you have light, you shine it, you create excitons everywhere. And these excitons are tiny, the Bohr radius of them are much smaller than wavelength of light. So then only the ones that are in the middle see that gradient. Remember, the beyond dipole, the quadruple transition depends on the gradient of the electric field. Back to quantum 101, right? So only these ones would see it. These ones don't see an appreciable field gradient. So that's why one would not see it typically. But what if I'm in the situation that the electrons are not bound? Imagine I have graphene, quantum Hall, and then you go and calculate this Fermi-Goldman rule. You have two Landau levels, 0 and 1. M is the index of the orbital in the symmetric gauge. So you go from these kind of orbitals to these kind of orbitals, and then the light has not only polarization, but an orbital angular momentum that is characterized by this L. So the selection rule will tell me that M plus L should be equal to M prime, but then the radial integral should tell me whether this is a small effect or a large effect. The QM calculated a bunch of Bessel functions, and then it turns out to be large. So this is this paper many years ago. Then we were trying to see whether there should be some experimental signatures of that. So experimental signatures of it, this is again the theory. Yes.
But as we look at these effects, am I still allowed to use error substitution, like minimal coupling that we're talking?
Which is minimal coupling, but it's D dot A,
But
not D dot E.
yes, exactly.
Exactly.
As long as I put A in there.
Yes, yes. So it is P dot A, but I don't replace it and then write D dot E.
Okay. I'm allowed to do like E minus A.
That's right. That's right. That's right. Yeah.
Thank you.
Sure. So now let's think this Gedanken experiment that will turn into a real experiment in a moment. So Correlated, very similar to the Lachlan pump. You have lights that is twisting left and twisting right. These are two Landau levels. This M is this orbital angular momentum of these Landau levels, Landau orbits. So you shine light with the non-zero orbital angular momentum. So you go from M to M plus 1 or M plus 2 or M plus 3. That's the excitation that is preferential. But then the relaxation is democratic. The relaxation does not, is like a Doppler cooling is like that. You preferentially kick them in one direction, but they diffuse in all directions. So you pump them like this, and then they decay like that. This is the population in Landau level 1 and Landau level 0. So when you shine light, you push them to higher and higher orbitals, and they will fall off your sample because it's a Gedanken experiment. So it is like really optical pumping. If there is a core atom person in the audience, this is exactly like optical pumping. Well, these are hyperfine state of an atom that you prepare it either over here or over there, depending on the polarization. You can go back to the envelope calculation and then calculate the radial current that is due to this illumination with non-zero orbital angular momentum. L is that number. So again, this is a long story. It started in 2017, but last year we just finished, and this is now published results. So the graphene for Kelvin, 9 for Tesla. You shine light with one orbital angular momentum. You measure the radial photocurrent. So this is the radial photocurrent over here. The current changes as a bias voltage. Bias voltage is a radial voltage. So you apply it, and then you see that it increases. And we have to do that because you will say, oh, you've tilted the system. That's why you had a current. But then you see that regardless of the bias voltage, we have some response. Now I change the light. It now rotates backwards. And then you see a difference. So the difference is, this is our signal. If it was just due to heating or just the dipole approximation limit, these two values should have been the same because the only thing that is different from them is the phase winding. If the electron is over here and then the light is winding like this and winding like that, it should not care about the phase profile of my light. So the fact that it's caring is that the electronic wave function is extended, so it would see the phase gradient of light. We do a bunch of control experiments. So this is the signal. So the difference between two is this is my signal. If you flip the magnetic field, it should flip sign because everything will just be flipped. So that's the case. We also do a polarization measurement. We change the polarization. We see that the difference does not change with the polarization. That's our signal. For orbital angular momentum 1 or orbital angular momentum 2, naively you would think that for 1 should be larger, should be larger than 2, but we have an explanation of that. It's just the spatial overlap of our signal. And then we are in the linear regime, so when you increase the power, this get increased. But we are kind of confident that if you keep increasing the power, at some point you should hit the Pauli blockade, but we are not in that regime. So this is for 9 Tesla and then -9 Tesla for both cases. Okay, so if you agree that this explanation is correct, so we have a quantum Hall explanation, but you can also write a simple Dirac-Fermion in a magnetic field. As long as you don't do dipole approximation, you get similar results. So this means that I have some response that is measuring the spatial coherence of the electron. If the electron was tiny, it doesn't have any spatial coherence, I would not see this. So maybe this at some point will be a way to measure the spatial coherence of an electronic wave function, of course, up to the diffraction. And then maybe I can now image some of these quantum Hall states. Maybe I can optically break them, etc. So this is kind of our first result that tells us, oh, okay, you're doing something correctly. The light can actually kick the electron and manipulate the external degree of the electron. And then there are some caveats in this experiment, etc. But I'll skip. So we are on time, and maybe I just say that the results of these things. So to optical lattice for 2D material, yes, it's possible. What's happened? I go here. I show just the references. So we have seen some signatures that we can actually induce some optical lattice for excitons. There's a lot to do, whether we can trap them, whether we can cool them, it's ongoing. I did not get a chance to talk about excitons in a correlated material, and I did not get a chance to talk about how we can optically measure some correlators, like the spin-spin correlator or spin-charge correlators, or some topological properties. But these are the references if you're interested. I thank my collaborators. This was a lot of work. So this is the topological frequency comb team. It was led by Chris Flower, and Mahmoud is a postdoc, and Lida is the younger graduate student who took over that experiment. And the blue is the team on the graphene, this orbital angular momentum experiment, and the red was the TMD and net correlated excitons that I did not get a chance to talk about. These are like most of it was actually collaboration, experimental collaboration with Yojo's group, and on the theory side with Jay Sao, Shankar, and Victor. So thank you very much for your attention.
Very much for your time for questions. It wasn't clear to me why this last effect requires coherence of the electrons, because your is already localized. Each orbital is localized.
So I'll repeat the question to make sure I understand. Imagine that my electronic wave function, because of disorder, etc., was completely trapped somewhere.
Well, but even without the solar line, my electrons is going around in circles.
Okay, so imagine that my electron is going in the center, so what's the question?
Why do you require coherence? Actually, you said that this effect requires coherence.
Because it's if it's then they would look as a like localized emitters. If there was no phase coherence, they were saying that if the charge was conserved, but the coherent length was nothing.
Yeah.
But again, how do I write my matrix element? It would be like a localized charge that is interacting with it's like a local emitter. It would not mean that you see what I mean?
Maybe it's like an orbital current that they can add up.
With no coherence. So charge is conserved, but the phase is not conserved. But how do I get the sensitivity to the phase of light? Because imagine that the charge is conserved, so it has no memory of what is the phase. So then why should it care that the light is circling this way or that way? That's your question, right? So my electron is going like this, but it's getting kicked with some dephasing mechanism that it loses the information of the phase, right?
No, I thought you were talking about spatial coherence.
The spatial coherence.
Yeah, but so electron here doesn't know about it.
Very good.
Every electron is going around in circle
Very
for
good.
a long time, but electrons very far apart don't know about the phase of each other.
So then in that case, how do they know that the light is twisting one way or the other?
Well, locally they know.
Locally, they know. So locally,
Going around.
so that's maybe I will make it clear. So the claim that we are making is that the electronic wave function is seeing the phase gradient of the electric field. So it doesn't have to wind around the whole of the core beam as long as it has some spatial extent. So this is the core beam, and this is the phase winding of this. So the electron can be coherent all the way, and we will see this effect, and it kind of agrees with, but it doesn't have to. As long as my electronic wave function is comparable to not LV, it should be large. If I put LV, I don't get any effect. So it has to be a little bit comparable to lambda, such that I see this. That's the whole point. Because naively, the first time that I discussed this with folks is that okay, LV is like 1 nanometer, and then you're doing an experiment that like 900 nanometers. So there is no way that your electrons would care about the gradient of the electric. But this is indeed the case. And 100%, I'm not claiming that the electron is coherent all the way around.
Yes, I misunderstood.
No. Yeah, it was the Gregorian experiment that led us this, but the alternative explanation is this, but still some spatial coherence. Very good, thank you.
So with the dimension of these structures matter, I mean, you need to, in a ballistic limit or I mean, does it matter? Have you tried to make these structures of different sizes?
No, we have not, and indeed, that's kind of like the follow-up, because right now we were limited by the size of our beam, because when you make a beam, the donut, the most naive version of it, the fancier version that they don't care. When I make L1, L2, L3, L4, they change size, so you have to make like samples that match the spatial form of them. But we have some other idea that does not rely on this Laguerre-Gaussian field to establish again this spatial coherence that they're saying.
But then the Cobina structure is still very small, right? It's just the center
Micron
point
size. Yeah.
avoids the singularity of the light.
Correct.
And the follow-up, you show that in these, when you have different orbital angular momentum, so somehow the photocurrent is larger for L equals to 1.
Yes.
And smaller for L
Yeah.
equals to 2. Do you have a
Yeah.
intuitive explanation?
So the explanation was just kind of related to the previous comment, is that when we made the sample is optimal for L equals 2. The spatial overlap is good for this one.
Oh, okay,
And the L1 is kind of small.
okay.
So that's why you get more.
Okay, so it's just experimental.
Exactly.
Okay, got it.
We are happy that the fundamental of the photon, right?
Yeah. So naively, the L2 should kick electrons further, so it should be like twice.
Right.
But that was not the case, so we had to.
It's just the
calibrate.
structure
Yeah,
itself.
yeah.
It's not intrinsic.
That's right, that's right.
Thank you.
I have a question about your third axis electron correlation.
Uh-huh.
Is it obvious that the electrons themselves are forming strongly correlated states? The light matter interaction will produce interesting states for the photons?
That's like part of my talk. It's good. The short answer is complicated, and one has to go case by case. The formation of these excitons on a correlated material, I mean, with the short answer is really that I cannot. But the nature of light matter interaction, first of all, is the same. It's just P dot A. I'm not claiming that QED is wrong. It's just you cannot think of them as just the binding of an electron and a hole like that. So in the case of a Mott insulator, if you put a Mott insulator over here, this will be sitting on a Mott insulator. So this will be like a doubler that is sitting on this. So it has some interesting effect. This doubler is moving. It can have some interesting spin physics. So it will feel the spin physics while being an exciton. So the diffusion of them should be modified dramatically depending on the charge or the spin order on that. So each case would be different.
Photons are really very similar to phonons,
That's
mathematically.
Uh-huh.
Could you talk about topological photons?
Yes. So indeed, if I in the linear regime, instead of solving Maxwell's equation, I'm solving a bunch of oscillators, linear oscillators coupled to each other. And the same way that we synthesize gauge fields for photons, one can actually synthesize gauge field for phonons. And then there are several groups actually that they showed. If you play with these resonators in such a way that simulates, let's say, a uniform magnetic field, if you excite one edge of the system, it will propagate around the edge. And if you excite it at like a bulk energy, then it will propagate to the bulk. So those are cool experimental actually demonstrations of that. The nonlinear part of it, however, I don't know. The phonons are also nonlinear. And the questions I was asking whether there are some nonlinear invariants, to my knowledge, that's an open question.
In some sense, this nonlinearity sitting not the photons, but sitting in environment. Photons are linear all the time.
They inherit the nonlinearity by interacting with matter. So that's kind of the y-axis by itself, as correctly you said, the photons don't interact well, they weakly interact. It's just they interact with matter, and then the back interacts with photons, so that's why we have an effective interaction with the photons. Thank you.